So what I want to talk about today is be thought of as under the umbrella of representations of families of groups. So there are certain groups that come in natural families. So for example, symmetric groups, going over all n. The general linear groups, all n's. The general linear groups over finite rings, for example, z modulo p to the kz. Or say continuous representations of GLn zp over the GLn over the p-adic numbers. And I chose these families of examples where there are relations between them. So firstly, as we saw last week, continuous representations of GLn zp is the same as representations of GLn z modulo pkz for all k. So basically these two families, they are the same. But when we fix k, we get a family of groups. If we specialize and we take k to be 1, then we get representations of GLn fp. And many reasons one can think about Sn as GLn where p is 1 if you look at the behavior of the degrees of representations. So these families are related, and it makes sense to study each family together, because once we understood representations of S million, we have a lot of insight. So we can use it to study representations of S million and 1. So yeah, family members, what do? They stick together. Or as my 5-year-old put it, my youngest daughter, in one afternoon where she was not fighting with her siblings, that the one thing that's good about family is that sometimes we get along. So so these groups, they get along together. And the main tool to pass from one group to another is induction and restriction. So just if L is a finite group, say L is a finite group, and inside the finite group G, and we can go from representations of L to representations of G. So all my representations are complex, and most of the time the groups will be finite, or sometimes they will be profinite. So we can have induction from L to G, which is given by we take a vector space and we send it to the CG tensor over CL of X. So we think about CG as a CG CL bimodule, and we got a representation of CG. And in the other direction, we have a functor going from representations of G to representations of L with a restriction, which we can also think about tensoring with a bimodule. This time we'll tensor with the bimodule CL CG, and we get the restriction. And if we look at these families, then suppose we know, so let's start with Sn. Of course, there are many things one can say about Sn, but I'm going to take some particular point of view. So suppose we know the representations of Sm for m smaller than n, for every m smaller than n, and we want information about the representations of Sn. What we can do, we can use induction from subgroups of the form S lambda. So suppose lambda is a partition of n. So lambda is lambda 1 up to lambda r. And S lambda will be S lambda 1 cross S lambda r. So we can embed this subgroup inside Sn. Now we know the representations of all these subgroups. We can induce from S lambda Sn representations of S lambda. So we take a representation rho 1 of S lambda 1 up to rho r of S lambda r, and we take the exterior tensor product, we get a representation of this subgroup, and we can induce it to Sn. In fact, for Sn, we can take trivial representation and go over all partition, and using the Specht modules, recover all the irreducible representations of Sn just from trivial representations of these groups. But when we want to recover them, once we induce this representation is highly reducible, we need to identify inside this representation the irreducibles that we are interested in. And so what the tool to study induction and restriction is the Mackey formula, or in this case, will be the Mackey theorem, which explains what to do when we want to induce from S lambda to Sn, then restrict, say, to another group S mu. So if we first induce from S lambda to Sn, we get a representation of Sn, we can now restrict it from Sn to S mu, and we can rewrite it as restriction and then induction. So that will be a direct sum of all the elements W in the double cosets Sn, S lambda, S mu. And then we start by restriction from S lambda. So we restrict from S lambda to S lambda intersection with Ws to W inverse. I'm sure you are very much familiar with this, but I will need this as notation. So it's a kind of a reminder, a gentle reminder. Now we can conjugate with W, and then we induce. By this conjugation, we came from a subgroup of S lambda to a subgroup of S mu. Now we can induce S mu, and we get a representation of S mu. So that will be the induction from S mu intersection with W inverse S lambda W to S mu. So go up, we go down, and then we go down and go up, but we need to go over all the possible representatives. We need to take into account all the possible relative positions of copy of S lambda and a copy of S mu. That's what the double coset representatives give us. All right. Now, the second thing that I want to talk about is GLn FP. So when we look at the family groups GLn FP, in fact, there's nothing special about P. You can do it every finite field. So we can try to imitate this process. So what would be the analog of this process? So again, suppose I know the representations of GLm FQ for all m less than n, and I want to say something about the representations of GLn FQ. This is very much related to the Penrose lectures. So the linguistic theory is a generalization of what I'm going to describe now, which is parabolic induction or Harish-Chandra induction. So naively, we can again take a partition of n and define G lambda as GL lambda 1 FQ up to GL lambda R FQ. This group embeds inside GLn. Let's call it Gn for now. So Gn is the group GLn FQ. We can take representations of these groups, the Levy subgroups. We know them very well. That's our assumption, and we can induce to Gn. And concretely, we can embed. We can think about these lowers general linear groups as sitting inside the large group as block element. Now, it turns out that if one induce irreducible representations of G lambda to Gn, so rho lambda again will stand for a tensor product or outer tensor product of representations of all these groups. And this induction becomes very messy, very difficult to control what's going on here. And the idea of Harish-Chandra fix this is, he said, slow down, you move too fast. Or maybe it was Simon and Garfunkel. Someone said this, to slow down. So what does it mean? We can look at the unipotent piece here, and we think about this subgroup as the Levy subgroup, and let's call this one U, and here the group is L. Then what Harish-Chandra suggested is to change the induction a little bit by extending the representation trivially from this diagonal, from this Levy subgroup to the unimportant part, obtain a representation of the parabolic subgroup, a very special representation. It's a representation that is trivial on this part, and then induce it to G. So instead of inducing and getting a huge representation, we take an intermediate step and we extend the representation trivially to U. In terms of the functors, that means that we change the induction to the map X goes from X goes to CG EU, and then we tensor with CL over CL X. So EU is the idempotent associated with U. And it's easy to see, and L normalizes U. So CGEU is still a CG-CL module. But it is a smaller module because we knocked out all the functions in CG that are not U invariant. So these are only functions in CG which are U invariant from the right. So this is a smaller module, and therefore we get a smaller representation, which is much easier to handle. In fact, what can be shown is the following, but maybe before, let me denote this induction by I, L, U, G. This is the functor. I need to know what is L. I need to know what is U. So, I mean, of course, I know what is L because that's the group I'm starting with, but I need to know U, and then I get this functor. And there's a functor in the opposite direction. So the reverse functor will be will be R G L U, which will take a representation Y of G, and we'll send it to the representation of L, which is EU CG tensor over CG of Y. So again, this is a CL CG module, and by this operation, we got a representation of G from a representation of L from a representation of G. And now what one can show is that if you take G lambda and you use these functors, I, G lambda, U. So for every G lambda, we'll have a different U. It will be U lambda that I need to take. So I G lambda, U lambda to Gn. I want to use this functor to go to Gn, then go back to G lambda. And again, I can go down and use the functor R and then the functor I. And what one gets, do you see still here? No. Okay. Okay, so now I'm going from G lambda to Gn, then to G mu, and I want to understand the functors I, G lambda, U lambda, Gn, and then I, G mu, U, sorry, R. And this can be written as a sum similar to this sum. I'm now just going to replace S lambda with G lambda and restriction with the functor R and induction with the functor I. So this is going to be a direct sum of R from G lambda intersection W inverse G U W. This is from G lambda, and then twist by W, then the functor I from G mu intersection with W G lambda W inverse to G mu. So first restrict from G lambda, then twist, then go back to G mu. But I haven't told you what are we summing over. And this is the main point of what Harish-Chandra did. It's no longer double cosets of these groups inside the P group, but rather a combinatorial set which is the same for all different fields. So the set that you see here is going over, not over the levy, sort of the different levies that we have, double cosets of the levies, but rather double cosets of the parabolic, which are much larger groups, and so the representatives is a much smaller set. So the set is, we go over all the elements in Sn modulo S mu S lambda. So double coset of the symmetric group is the Weyl group in this case. Which means that the symmetric group controls the relationship between these two functors. And so what happens is that now one can ask which representations can be constructed using this machinery. One can do the bookkeeping thanks to this formula over there, which is combinatorial. And the next question is, which representations we didn't cover? And these are the Cuspidal representations. And as Dipendra told us, it's difficult to construct the Cuspidal representations, but they have a very nice parameterization. They probably don't have time to say much. So the Cuspidals, so those that you cannot construct in this way, they are in bijection. So let's say the Cuspidals of Gn, they are in bijection with characters of f q to the n star, sort of characters of the highest field extension that you can squeeze inside GLN, but special characters, those that do not factor through the norm map from FQN to FQM, where m divides n. So these we do not take. If the characters that factors, we do not take them. And there's also relations between them, and we need only Galois orbits of these. The Galois group FQ to the n modulo FQ over FQ, and we take orbits these characters. And so what happens is that the theory for the representations of GLN FQ breaks into two components. One component is geometric, sort of we think about Sn when we take higher values of n, and we induce. That's one direction, and the other direction is controlled by the algebraic closure of FQ and somehow these characters. So I should take star here and characters, but let me not do this. But so there's an arithmetic direction, and there's a geometric direction. And the theory really breaks into two in any possible meaning that you can think. So if you take a Cuspidal character of any of these n's, and you start inducing it further, it will behave exactly as the trivial character of Sn evolves when you induce representations from Sn to Sm, where m is greater than n. And there's a beautiful exposition of this theory by Zelevinsky. This is lecture notes in mathematics. It's 6.9. Where he collects everything I said now into a giant Hopf algebra and really shows that this is exactly what happened. But now I want to move to the other classes of groups, which are representations over the rings. Any questions? So now it's GL and Z modulo P to the KZ, or GLN ZP, and then we think about continuous representations. So if you start with a naive approach, saying that you take products of these groups, so that will be GL lambda 1 over the ring, etc. And again, you think about block, embed this subgroup as block block matrices inside the P group, but now over the rings. And think about this unipotent subgroup and define exactly these functors. You get again a big mess. Even much worse than the mess that you get here. And so the idea of our work is to somehow follow Harish-Chandra and slow down even more. So it depends on P. Firstly, it depends on P. But what happens if you looked at the relative position of two flags over a finite field, then these relative positions are measured by the symmetric groups. The only thing you need to know is the dimensions of the embeddings. If you look at the double cosets of the Borel of the, I don't know if we should call it the Borel, but the upper triangular matrices, and you do this for G mod B, now over the ring, then the relative position of two, so what you're looking at now is you have G mod B is the space of free flags, and you take a free flag and you filter it with another free flag. The problem is that now the intersections, they are not free anymore. So in particular, when you look at the relative position of two flags, you get intersections and embeddings of many submodules, which before they were vector spaces for the finite field, but now they are modules. And the problem of classifying embeddings of modules is a wild problem, just pair of embedding of modules. It is a wild problem. So let alone such a table. So it becomes something which there's no evident structure that one can hands on. That's right. Exactly. Exactly. Sorry? Yeah. Depends on P. Everything depends on P, and in a very unpleasant way. Except for GL2. Okay, so what we want to do is to slow down even further. So suppose this is our levy, and we want to induce to a representation of GLn ZP. Then we have this upper unipotent, and we also have another unipotent, which is the lower unipotent. And there is no difference. I mean, we could do the whole theory here or there, but once we combine them, then we reduce significantly the problem. So what we are going to do is the new functors that we are going to define. So these are functors that go from presentation. So let's call this one L. This is the subgroup. And I'm looking at I, L, U, V, G. So this will go from representations of L to representations of G. And it will send a representation X to C, G, EU, EV, tensor CL, X. So this is still a CL module because L normalizes both V and U. So this is a CL module, but it is smaller than CGEU. In fact, significantly smaller. So this is one functor, and there's a functor in the reverse direction. R, L, U, V, G. Go from representations of G, representations of L, and that will be tensoring C with EU, EV, CG, CG. So now this is a left L module, and so we got a representation of. Now it's important to know that these idempotents, they do not commute, and so this product is not a new idempotent, it's something else. So what can we say about these functors? So before that, I need a definition. So G be a finite group. L, U, V subgroups of G such that L normalizes U and V. Exactly as we have. We say that U, L, V is a virtual Uri composition if the map from U cross L cross V, the multiplication map, G is an embedding. So this is the product map. U, L, V goes to U times L times V. It's important somehow to keep track about the fact that all these groups, they are compatible with each other. One reduces to the other. So to maintain compatibility, it's very important to think about the GLn ZP, so the profinite completion. So let me adjust this definition a little bit. So let G be a profinite group, and LUV be closed subgroups. Then ULV is a virtually Uri decomposition if one, this is an open embedding. And the second thing, which we do not see at all in the finite case, there exists arbitrarily small open compact K in G, such that if we restrict this product map to the intersections, so we look at U intersection with K, and then L intersection with K, then V intersection with K, and we map it to K, again by the multiplication, by the product map, then this is a homeomorphism. So this is something we only see at the profinite level. So let me give you an example. So if the group is GL2 ZP, and you look at the groups 1 ZP01 cross ZP star VP star cross 1 Z1, you map it by the product. These are all closed subgroups, and this is an open embedding. If you restrict attention to the groups, invertible groups that looks like this subgroup. So these are invertible matrices, but we know that the left corner here is divisible by P. This is the Iwahori subgroup of GL2ZP. That's the source of the name. Then in this case, when you look at groups 1 ZP01 and you multiply them, but now you take 1 and PZP, and you multiply them, then this is a homeomorphism. So this is an example of a Iwahori decomposition, and this map is honestly an homeomorphism. And this is a virtual Iwahori homomorphism. It's a decomposition. This is an open embedding. It doesn't cover the group GL2ZP, but it covers a large part of it. Okay. So maybe now I can write several theorems. No questions. Sorry? One. We thought about it a lot. I don't remember the answer. I think we didn't see how to prove it, and maybe we had an example. So maybe we can talk about it later. But I think we needed this condition. This is a very natural condition. So for example, this condition is satisfied by all compact subgroups of reductive groups of the p-adics. So there's a very large family of such groups that satisfy this. Okay, so I forgot to say things. So here's a remark. So first thing is that these functors are harmless. So it's important to know that we didn't do any damage. So what I mean is that if K is 1, and we now have two competing definitions to the representation theory of GLN FP. Harish-Chandra, original definition by tensoring with C, G, EU. And the new definition now that says that we tensor with this group. And we certainly don't want to touch Harish-Chandra. There's no way, yeah? Nobody is suggesting this. So it's good to know that there's a theorem by Howlett and Lehrer that says that these two functors are isomorphic for the special case of K equals 1. So no harm is done for the known case. So this is a theorem. These are isomorphic by Howlett and Lehrer. So they looked at something else, but one can translate what they did exactly to this result. And the second thing is that these functors are compatible with reductions. These functors compatible with the reductions. So this remark is really concerns the family of groups GLn Z modulo P to the K. If you define these functors with respect to K and then with respect to K prime, and you have the reduction maps, then it doesn't matter if you first use these functors and then reduce, or first reduce and then. Okay, so let me just end up by quoting a few theorems. The theorem is that under all these definitions and assumptions, I, L, U, V, G is isomorphic to I, L, V, U. So you can swap the order, it doesn't matter. Second is that I, L, U, V, G are L, G are B-adjoints. As the Harish-Chandra functor and as usual induction is. Now, sorry? So left adjoint and right adjoint. The third thing is one of the most important properties of these functors, and it is the following. So I, L, U, V, G takes finite dimensional irreducible representations, irreducible or not, into finite dimensional. So if you think about the original Harish-Chandra induction, the other problem, other than the double cosets that I mentioned, that you cannot decompose the representation in a nice way, the other problem is that if you take a closed subgroup and you induce to the group, you get from a finite dimensional representation suddenly an infinite dimensional representation. We don't want that. But these functors, once we use the two idempotents, they get rid of this problem once and for all. So finite dimensional go to finite dimensional. I will not take more time. I'll just say that these functors, they are compatible with Clifford theory. So if you do Clifford theory on G and Clifford theory on L, with respect to some normal subgroup, and you can induce before, you can induce after, you can induce from the stabilizer, you can look at projective representations of the quotient of the stabilizer of representation to projective representations of the stabilizer of the image modulo a subgroup, modulo the normal group, and these are also compatible. And whenever the orbit method applies, it is also compatible with the orbit method.